controller loops. Okay, so we have seen open loop, and let me to record the thing first. Okay, so today's lecture is about frequency response analysis of both closed loop and open loop. But today we will be focusing on open loop only. So we will be looking into how the controller, doesn't matter proportional controller, integrated controller, or even the combination of all three controllers, how the response will be plotted in a frequency graph, or we call that amplitude versus the frequency graph or the time graph. And then we will analyze the graph, how to get the important information from them. Okay, so with that, we also will be looking into the Ziegler, Nicholas, and Cohen-Poon tuning method. So these two are very famous method, or successful method, we can say, to analyze tune feedback PID loops. Okay, focusing into how to get controller gain, integrated time constant, or even the derivative time constant, the tau d, from these two methods. Okay, right. So this is an example of block diagram shown here. For us to analyze the frequency response from any loop, doesn't matter open loop or closed loop, first we need to simplify this diagram into one single diagram. We need to reduce all this diagram with just one input and one output diagram. Okay, if you notice here, we have transmitter functions, feedback loop, and then we have a controller gain, and we also have a disturbance introduced into this. So the signal from this block diagram, or we can say the controllers loops, basically will be in the form of input sine wave, okay, versus the frequency in radian or time term. Okay, and then we also will have output signal terms, response in a sine wave also, same frequency, different amplitude and phase. So we will be looking into these two. So from here, we also will be looking into a board plot, we call that, of amplitude ratio versus frequency, or phase versus frequency. So the frequency graph difference and the board plot difference is that frequency graph, okay, frequency graph, you will be having amplitude versus time. Okay, we'll be having a frequency graph or plot like this. This is for input, let's say, and output maybe will be something like this. But when it comes to, this is frequency response. Okay, when it comes to blot response, blot will be basically amplitude ratio versus frequency. All right, or another plot, phase versus frequency. So in frequency response graph, we will be having two plots in a single diagram, but in board plot, we'll be having two plots in two separate diagrams. So that's the difference between board plot and frequency plot. Okay, so what is blot? I mean, what is frequency basically means? Okay, frequency is basically meaning the oscillation shown here, the oscillation shown here. Okay, from here, or we also call that as sinusoid. Okay, so from here we can determine which one is the input signal, which one is the output signal, and so on. So frequency response is basically a response of output variable to a sine input. So the graph, the shape of the graph, we call that sine wave graph. Okay. What is frequency response? Basically, it is how a system responds when it is excited by oscillation of different frequencies. And why is it very useful for us? We can use the information, or it can lend informations and powerful control design techniques for us to analyze. Okay. Now, frequency analyze, after a long time, the output frequency will be the same as input frequency, where output response is also a sine wave. So if you notice, this is the smaller graph is the input graph, and the taller one is the output signal wave from the output system. Okay, so from here we basically can calculate what is frequency and what is the amplitude from here. All right, so basically the amplitude can be calculated from this axis to the peak, or the other way, from this axis to the peak. So different graph will have different amplitude. All right, so that is one thing. Another thing is, if you notice, as time goes on, the oscillation trend or the gap is like fixed. Okay, so we call that fixed phase and gain shift for larger times. As time goes on, it will be remain constant. So this is about a sine graph, frequency response graph, or we call that sine wave graph. Okay. So let's say we have a response. I'm just giving an example. Let's say we have a response of a system in a sinusoid form. Let's say our input as U in terms of, okay, I have a controller system, input as U and output as Y equals to dA sine WT plus the argument. All right. So if you notice the input, the difference between the input and output, I'm going to have additional amplitude term here, and also additional argument term here. So basically, for us to define output, we need to find out what is amplitude and the argument of this. Okay. So the input and also the output will be plotted at the same graph. So from there, we can notice, for example, let's say this is input graph, and let's say this is output graph. Okay, all right. So from here, we will know that both input and output oscillate at the same frequency, meaning constant frequency. All right, and the gain, the gain of the amplitude, we call that AW, is the ratio of output over input amplitude. Okay, and the phase, or we call that the argument, is the phase difference between two signals. Difference between two signals. Okay, so this is about the frequency response. All right. So again, like I mentioned just now, so this is two different graphs. They separated, but it's supposed to be in a single graph. So this is just separated so that we can visualize the graph easily. So we have input graph. Okay, input graph. The amplitude here is A, and the output graph, the amplitude here is B. So the amplitude ratio will be output over input amplitude ratio. So the output amplitude over the input amplitude, and the ratio is the amplitude ratio. And that is one thing. Second thing that we can get from the graph is the argument, or we called it a phase angle. Okay, so phase angle from these two graphs can be calculated by finding the difference between the peaks, first and second peaks, or it can be the other way, to second to third, third to fourth, and so on. Anyway, the value going to be same because their frequency remains constant. So the difference between the peak output and peak input, this thing we call it as phase angle. So where to apply all this, we can get from, we will be looking into that later. Now, the trend of the frequency graph varies from one system to another. Okay, let's say I have a signal in terms of the sine t. The graph will be different from the sine t3 graph, correct? So the sine wave for this and sine wave for this will be different. Their amplitude will be different. Their frequency will be different. Their angle will be different. So this is just for your knowledge. Now, open loop frequency response. What they mean by open loop frequency response? Like I mentioned, this is actually a feedback loop controller system. Okay. But for us to analyze the frequency response, we need to reduce everything into a single input and single output diagram, in which we need to eliminate or apply the knowledge of reducing a block diagram and then come out with one single block with one input and one output. So when they say open loop frequency response, it can be used to predict the behavior of a closed loop system, basically. So from here, we can conclude what the closed loop system is, or the stability of the closed loop system. The frequency response method, this method may be less spontaneous than other methods. Even then, it has certain advantages, like in real life situations in which we can use for modeling transfer functions from normal physical data or experimental data. Okay. Now, okay, how to get the amplitude and the argument? Let's say right. All right. Let's say we have an input, like I mentioned just now, our input. So whatever I'm mentioning here going to be the summary of the next few slides. So the input is defined as sine frequency times the time. And let's say the output is expressed as y equals to a sine. Now I have added an new term amplitude here, and also the additional of an phase angle term in this output expression. Okay, so from here I know the gain is basically the A. Okay, and that is basically function of the frequency. Now the phase from the function I can calculate is the argument. So it is expressed in terms of this. So these two basically depends on frequency. Okay, frequency meaning the oscillation in the graph. Okay, it varies from one type of graph to another. Now, how to calculate the gain? The gain A. The A basically can be calculated by finding the modulus of the function in terms of JW. All right. So, and then the arguments or the phase angle can be calculated by finding the argument of the same JW function. Now, what is the meaning of this? Let's say I have an example. I'm giving a transfer function example as 3 over s plus 2. Okay. First, I need to convert this function in terms of g, j, w. So wherever I have s, I need to replace with jw first. So this will be jw plus 2. Correct? So from here, I need to find the gain AJW. If you notice, the formula to calculate the gain is basically the modulus of this function, right? So the modulus is basically can be get from square root of W square plus 4. So I need to take the W and the 2. The J I'll be ignored. Okay. So this is to get the phase, the gain. Now to calculate the gain, I need to find the argument of the function in terms of JW. So how am I going to calculate that? The basic formula to calculate the angle is negative tangent from, to calculate the angle from a frequency graph is negative tangent W, okay, over the 2, the constant at the denominator. Okay, so this is the formula to calculate. This is just an example for you to try. Okay, and we have not necessarily all the transfer function will be in this form. It can be different form as well. Like we have, let's say, plus something, 3 plus something, and then here maybe s plus 3 and here s plus 2. The method to find everything is same, but just that remember the definition to find the gain and the argument. So argument is basically the difference, right? Difference between the numerator and denominator, and for the gain it remains the same, right? Now, open loop frequency response. Just now, the open loop system that we saw, this is the standard formula to calculate the amplitude ratio and the phase angle. Okay, so this is the gain and this is the angle, phase angle. Right? So the amplitude ratio is in terms of K over the square root of JW. This is JW here, and the constant here plus another constant. And here, same method, same formula, tangent -1 of negative tau W. Now, if you notice here, the tau here is tau here is 1. Okay, at this portion, if you notice here, the tau is 1, not the J. Right. So for a first order system, okay, let's say we have a system in series, we can express that separately also. So for us to calculate overall amplitude ratio, we need to get individual amplitude ratio first, meaning individual amplitude ratio of this, individual amplitude ratio of this, and individual amplitude ratio of the third term. So it will be a product multiplication of all these amplitude ratio. That is for gain. Now, when it comes to overall phase angle, it's going to be the sum of all the phase angles. So I need to find phase angle for first term, second term, and third term separately, and then I'm going to sum all of it. Okay. Now, if you notice the negative inside here, somehow when you rearrange, it will become negative something. So the sign here will also change later on. Okay, so this is for the first order system. Now for the first order system, there is also another term, we call it as dead time. So what is dead time? Dead time, we always compare the dead time with lag time. Okay, lag time means time response from a process in which, for example, the initial effect of a change in control output can be seen immediately, but the final effect take time to develop. But when it comes to dead time, that is totally different or contrast from the lag time. Okay, in that time, we define the dead time to a period of time during which the change is manipulated immediately. Okay, so meaning for some time before showing a response, there will be some portion of dead time. Okay, so we can actually basically define the dead time or illustrate the dead time in terms of time graph for us to imagine. I can put that in. Let's say this is a pure dead time response. I'm going to have some response. But if you notice, before I give signal, this is the input, okay? Before the output response is out, there will be some lag, okay? Some dead portion at this part. We call it as dead time response. Now, how to define the dead times? Dead times is basically the similar to the previous one, output over input also, okay? But their definitions or the function will be different. Now, for dead time, the amplitude ratio remains the same, similar to our frequency analysis just now. But when it comes to angle, okay, it's going to be different from the previous one, in which earlier we only had the tangent term, correct? Now we're going to have additional term here, okay? Frequency times the phase angle, okay? And the frequency and the phase angle must be in terms of radians, so that when I apply the tangent, I can solve it correctly. Otherwise, your answer will be wrong. And for example, if let's say the term is not in radians and it is expressed in hertz, okay, or we call that second per second, we need to convert this unit to radians. So that can be done by multiplying with 2 pi to get in terms of radians. Okay, so this is about dead time. So if a problem mentioning that we have this controller system and then provided with a dead time of this much, this expression, we need to consider the dead time as well. Okay. Now, when it comes, before moving into the board diagram, the dead time response is actually delayed for some time after the output makes its step change, right? So there's a period of time where the dead time response, nothing, I mean, there will be zero response following the output step change signal, okay? So it also, we can call that as transport delay, okay? There is some delay in which the mechanism of dead time always caused by the transportation of material at some certain speed or across time, over the time, okay? So the dead time is basically a very important parameter for us to consider before analyzing any amplitude ratio, amplitude response analysis. Okay, a basic example I can give for us to imagine is like the baking process lah. Okay, we have some dead time for the cookies to absorb the heat from the oven. Okay, we on the oven, we let the oven to heat. After some time, only the cookies will get the heat from the oven. Meaning the transfer time or delay time between the or the process occur between the oven and the cookie, we call that as dead time. That's a very basic example that I can give lah. All right. We other than the frequency graph or amplitude frequency, amplitude time graph, we call that. We also have Bott diagram. Bott diagram is basically a graph of frequency response of a system, okay, in which we're going to have two separate graphs, okay. Like I mentioned earlier, we will be looking into two separate graphs. Here, amplitude ratio versus frequency, and the other one is phase angle versus frequency for open loop frequency response. Open loop frequency response means the reduced diagram, the final diagram. So there's no feedback loop or anything. We're just going to come out with one single diagram, right? One single block diagram. So we call that as open loop frequency response. Okay, so this is the summary of what I mentioned. We have amplitude ratio and phase angle, and the frequency here expressed in terms of radians and not radian over time and not frequency hertz. Okay, so this is the two diagram. All right, the sample of two diagram. Now the Bott diagram basically. We can get information directly from the Bott diagram rather than analyzing the frequency graph just now. Here we already have separate graph ready, so we can straight away calculate the amplitude of the gain and also the phase angle. Like earlier, we need to calculate, right? Now, Bott stability criterion. The Bott stability criterion basically has two advantages, okay? The criterion provides exact results, okay? It provides exact results and not approximate results for process with time delays. So that is one advantage. The second one, it measures the relative stability rather than just some softwares will give for a 0-1 response, right? For example, if you ask whether the system is stable, it will say yes or no only. But here it will provide you relative stability rather than just a yes or no response. So for stability, the overall amplitude ratio must be less than 1. Okay, meaning for us to conclude the system is stable, the amplitude ratio must be less than 1. So this is one factor that we need to consider. And secondly, the open loop phase shift must be equals to negative 180 degree or negative pi radians. Okay. Now the frequency in this system, we call it as critical frequency or ultimate frequency. Okay. There is another tuning method who expressed the critical frequency in terms of ultimate period. We call that as Ziegler-Nicholas. So what is Ziegler-Nicholas has mentioned, or we call that Ziegler-Nicholas method. Okay. In Ziegler-Nicholas method of tuning the controller, basically it is conducted by setting the I and D, the integral and the derivative controller gain to 0. We need to tune that into 0. So meaning the proportional gain, the KP, the integral and the derivative gain will be set to 0. The proportional gain will be increased until it reach ultimate gain. Okay. So this is about Ziegler-Nicholas tuning. So when we increase the proportional gain until it reaches the ultimate gain, we can see the control loop has stable and consistent oscillations. Okay. So this tuning can be done by two methods, either by experimental method or theoretical. Okay. The theoretical method, we also call that as frequency response to find the ultimate gain. Right. Now, for the experimental method, for the first method, we make the control action proportional only. Okay. we assume it is only proportional because the other two we always going to put as 0. So switch off or minimize integral and derivative actions. Okay, this is like by experimentally being done. All right. And then for the KC, we're going to give constant amplitude as oscillation, meaning the frequency we're going to make it constant. Okay, so at this value, the gain will be expressed as ultimate gain. Okay, and the oscillation period we call it as ultimate period as a time. Now, when you apply the Ziegler-Nicholas method, experimental method, here the response will be expressed for controller gain. For the proportional controller only, it will be 0.5 KU. So this is the rule of thumb. This is the basic rule that we need to follow. And for proportional and integral, the controller gain will be expressed as 0.45 KU. KU means ultimate gain. And for PID controller, it will be expressed as 0.6 KU. So these are the rules for us to express the controller gain. Okay, so rule of thumb we can say. All right. So the if you notice here, the KU is the ultimate gain and PU is the ultimate period, right? So how to calculate the PU will be 2 pi over the critical frequency. Okay, so this can be calculated with that. And if you notice, all the TI and tau D expressed in terms of PU only, and K, the gain, controller gain, expressed in terms of controller ultimate gain. Okay, KU. All right. So what is TI here? TI here is the controller's integrated time constant. Okay, integrator time constant, and the tau D here is the derivative time constant. So if you notice, when it comes to integrated, the P will the proportional controller only term will be nothing, no expression. Okay, just the controller with integral controller will be expressed, and similar for the derivative time controller, in which the derivative remains 0, right? So the D term will be nothing, and here the PI also we don't have derivative term, but PID we have derivative term. So this is like a formula to express the controller, the time constant, the integrated time constant, and also for the derivative time constant. All right. Okay. Now, at ultimate gain means the KU. Okay, KU. At KU, basically the system oscillates. Okay, and here the damping coefficient will be 0. You remember the damping coefficient will be equals to 0, and we call that as undamped system. So what is undamped system? Any undamped system will vibrate continuously without any additional applied forces. There's no additional forces, no additional. If there is, what will happen if there is an additional forces? The frequency or the vibration will not be same trend or same value. Okay. Now, the second method is the theoretical method in Ziegler-Nicholas methods, or we call that frequency method. Okay. We can derive this by theoretically perform the transfer function. Okay, so in theoretical Ziegler-Nicholas method, we have based on board stability criterion, the overall amplitude ratio must be less than 0. This is same for the experimental method and also for the theoretical method. And also the phase shift will be negative 180 degree. Okay. The first step to for the theoretical response analysis under the Ziegler-Nicholas method, we need to find critical frequency and ultimate frequency. Okay, in using the open loop phase shift. All right. So the phase shift expressed as negative 180 degree, right? So with that, I can calculate the angle already. All right. With angle, I can find from there, I can calculate the PU also, ultimate period, by using 2 pi over the frequency, critical frequency. All right. So use this term to calculate the use the phase angle negative 180 to calculate the critical frequency, and then we can solve the entire equation. And that is for first step. Second step, next we need to calculate the KU, the ultimate gain, using the amplitude ratio. And then we also need to calculate it by equating equals to 1. Okay, the Y1, the basic rule, it must be, the amplitude ratio must be equals to less than 1, right? So when it is less than 1, this is the basic requirement. So when I equate 1, that means it already more than 1 already, above the maximum value. So from there, I can conclude what is my amplitude, ultimate gain is. Okay. So again, we can use the rules to set the controller gain. And lastly, we need to calculate the Kc, tau I, and tau d based on the type of controller that we are discussing. So the basic rule will be similar to the earlier one. Just now, the Ziegler-Nicholas method is the one of the tuning method. Okay. The second method is the Cohen-Kuhn tuning method. Right. So in Cohen-Kuhn tuning method, the amplitude ratio requirement or the rules will be the same. Must be less than 1, and the phase angle must be equals to negative 180 degree. So let's say we have a diagram open. We need to express everything in terms of open step response. So we need to do in a single diagram and all that. Okay. So we need to reduce the entire block diagram into a single diagram. Now, when it comes to Cohen-Kuhn method, the open loop is modeled as first order plus dead time. Okay. So when you reduce the diagram into open loop, so we consider that as first order plus the dead time. It is not just the first order plus the dead time. Okay, so the basic rules for tuning the parameters will be for the Ziegler-Nicholas method will be different, and for the Cohen-Kuhn will be different. Okay, so here if you notice their gain, okay, their gain is expressed differently, and R can be calculated by dividing the angle with tau time. Okay. And when it comes to integral, the proportional controller don't have integral, the PD controller don't have integral, and derivative, the PI don't have the integral derivative term. So only expressed for PD and PID. Right? This is for Cohen-Kuhn. The Cohen-Kuhn is just for our knowledge basically, because compared to Ziegler-Nicholas method, Cohen-Kuhn is not used that much. But then Ziegler-Nicholas is more apparent. Right? So when you are tuning control loops using Ziegler, Nicholas, and Cohen-Kuhn, both are very excellent way to start with. But further optimization is possible, okay, in which high performance situations or critical control loops appears. We need to optimize the conditions for both Ziegler, Nicholas, and also for Cohen-Kuhn methods. All right. So this is the today's lecture is all about. Any question you can ask me? Yes, I just seeing only your message, Shelby. Same link for lecture. I use the same link. Okay. If there's no question, we can end the session today, and I'll upload the tutorial session, question and answer. Okay, you can refer to that. We'll be seeing next week, Monday. Okay. Thank you for your time. Bye.